welcome, welcome on the coldest day of school here. Yep, yep. Okay. I'm glad all of you made it with all of your fingers and toes and most of your nose. This morning we're going to finish our discussion about water pollution. We have 3 last topics to cover with this, most importantly of which is eutrophication, the pollution of nutrients in water bodies, which will lead us to finally be able to talk about this image, which has been on both today and Tuesday starting with this slide. As you are chomping down on your snack, if you need another one, please come up and grab one. See if you and the person next to you can answer these 2 questions that relates to information we talked about on Tuesday. Give me a reason why plastic trash is a problem for organisms, and then see if you can name 2 toxic chemicals. We talked about a range of toxic chemicals on Tuesday. Can you name 2?
And the other one, 3-letter acronym.
There's lots of it.
BPAs, I remember because that was the baby bottle craze when
I
my
know,
youngest
yes,
was born.
exactly.
Let's see. Is this a turn in for participation?
No.
Okay.
This is a
Okay. I
warming
have
up to the class order. Make sure that everybody's
I'm Madison. Don't have to feel bad about not remembering my name.
I'm the worst. I remember faces. I don't remember names, just not much good.
I'm pretty much the same.
Okay, Rebecca. Dioxins, PCBs, BPAs. I just remember. What did I tell you?
I agree with the spirit, like I know exactly where you're coming from.
Why is plastic solid waste trash a problem?
My first thought was the sea turtle eating that plastic bag.
Yeah.
And also, doesn't it also affect like, it affects like everything.
Yeah.
Okay. Can you tell me why plastic trash is a problem? Willow. They eat it, and what's wrong with it when they eat it?
They starve to death.
So yeah, we can have starvation, and it can be toxic if it does actually start to break down in their system or gets entangled in their intestines. Caleb.
They can create an ecosystem, and then when that ecosystem starts to break down, like toxic chemicals come out and kill them.
Good. What else? What else?
I mean, it can kill them by when they get tangled and they can't swim.
Right. What does it do to us? What does plastic trash in the environment do to us?
Mango's not.
Gross us out because it's a big cleanup.
Good. Okay, it ruins the aesthetics. It's habitat degradation, both for the organisms that are in it, kind of all these reasons, but also for us. We talked about 4 big problems that are related to water resources, right? Water scarcity, drought, the overabundance of water flooding. We're talking about water pollution. The 4th one is habitat degradation, habitat loss. Okay? Recognize that all 3 of the things that we're talking about before we get to habitat degradation cause habitat degradation. Okay, they're part and parcel of the system. Anything else about plastics? One thing that, what was that?
They're persistent.
Good, that's what I was gonna put at the top. The reason they're so problematic, oh, the breed's running out. Okay. The reason that they remain in the environment to be ingested, they are out there being gross and ugly, degrading into toxic compounds, entangling organisms, causing death in one way or another, is because they're persistent, because they last for a long time. Okay? That's to our advantage. We want plastic materials that are going to last for several uses, that are going to be around for a while, so we can use them as storage containers. They can hold food and water for us. We can use them in all kinds of cooking and shipping applications. Okay, that's on purpose that they're persistent. But then when we're done with them, they continue to be persistent out in the environment once we're finished using them. And then they become a problem again. All right, can you name me 2 toxic chemical pollutants? BPA, good. And BPA is recognized as a carcinogen. You have to have, again, with toxic chemicals, and we're going to talk about environmental health hazards on your desk homework, it's all about dose, okay, when it comes to kind of risk of exposure to these chemicals. So how much are you getting in what period of time? Okay, so low quantities of BPA are not going to be terribly toxic, particularly to a healthy adult, but high quantities of BPA can cause cancer, definitely in laboratory mice, potentially also in humans. Exposure to BPA chemicals, which is used in some kind of plastic end use, both production of plastics and then kind of the end use preparation of it before it's going to go out for consumers. We don't know the consequences of long-term exposure to low doses of BPA in humans. Like, we're the generation that is that experimental cohort for that. Okay, what other things can be toxic chemicals? What about oil? Elena, did you have your hand up?
Yeah, toxic metals.
Good, and what kinds of metals?
Mercury, lead, industrial waste, and hydraulic fractures.
Good. Cracking liquid, okay. Any other toxic chemicals? Yeah.
Pops.
Say it. Elena and then Morgan.
Oh, sorry, there's my
Go ahead, Elena. POPs. Persistent organic pollutants. We're going to say Morgan. DDT. Okay. And DDT is one of those persistent organic pollutants or POPs. Good. Again, persistence is the difficulty with these compounds. They last when we're using them in industry or as certain types of pesticides. That's again on purpose. We want them to last for a long time so we can apply them once and they do their job, either in the manufacturing process or out in the environment where we're using them. But then they go on, okay, and they last for a long time in the environment. It's very difficult for them to biodegrade among these instances. And the conditions in which the spill or the exposure to the toxic chemicals can affect how long they last out in the environment. And that's where a bunch of the risk comes in. The other thing with toxic chemicals that you have to remember is that for many of these compounds, excuse me, particularly for the ones that are newer on the market, that are used and developed for manufacturing processes that are for new products, we haven't run the test to see how toxic they are. They're presumed safe until they're shown to have an effect on humans or organisms out in the environment. And this is how we get ourselves in trouble lots of times, is that we start using a compound and it gets released into the environment and we have no understanding of what its potential consequences are. And then come 10 or 15 years later, we have a big problem. We have a location, an industrial site that's become heavily polluted with a compound that now we recognize is fairly toxic in one form or another. But we had no idea when we first started using that compound that it was potentially toxic, and so we used it a bunch. And that's a principle that has to be changed, especially when it comes to toxic chemical release, both in terms of water, air, and land pollution. We have to start asking our manufacturing processes and our synthesizers to prove that compounds are safe first before they start using them, rather than having the burden of proof beyond scientists and health researchers and epidemiologists to say that there's a problem with a particular compound. And that's a shift in thinking. Okay, it comes from all these instances when we look back at these Superfund sites and say, this was a really bad idea. How come we started doing it in the first place? Well, because we thought it was safe. We thought it would be okay. And we've got to change that mindset to, is this going to be okay before we do it? Okay, and that can prevent a lot of the problems that we see today with these types of pollutants in all the situations I talked about. Guys have any questions about what we talked about last Thursday? We started talking about pollution. We finished up with flooding. We talked about sediment pollution last Thursday, and we did solid waste and toxic chemicals. Nope. Okay. All right. Let's do it. The three things that we're going to talk about today are heat, pathogens, and nutrients. We're going to start with heat. It's kind of the quicker one, and then the idea of pathogens and nutrients we're going to link together under the topic and heading of both fertilizers as well as sewage is the really big one. And we can think of sewage then in terms of both human and animal, solid and liquid waste, and it causes problems with pathogens as well as nutrients in terms of pollution. Heat pollution is the one that is a little bit different, I think, from this group of pollutants that we've been talking about. Particularly on days like today, we're like, heat pollution sounds like a great idea. Okay? Doesn't seem like this could ever be bad. But that's something that I want you to recognize, kind of like with sediment pollution, that too much of a good thing can be bad, or too little of something. There can be cooling instances in terms of pollution, temperature pollution. That can also be bad, particularly for an ecosystem perspective. Okay, so our first topic today is thermal pollution. And again, we often think of this as temperatures that are too warm as heat pollution for an ecosystem. But thermal pollution is really any change in water temperature that's beyond normal for that particular ecosystem. And it can be hot or cold. And again, most frequently it's hot. And again, we think of thermal and heat pollution in these types of instances. But I'll give you an example of cold water pollution as well. Where does thermal pollution come from? By and large, here in the United States, our sources of changes in temperature for freshwater ecosystems and even some nearshore coastal marine ecosystems is coming from industry and power plant coolant usage. They bring in water in order to cool down, to absorb heat from their manufacturing process. In terms of electricity production, the evaporation of water into steam and then that high pressure steam usage is what actually generates the electricity. It's vital to the energy transfers for electricity production. That means that they have a ton of hot water that comes out of these processes. And in general, they just release it into the environment. Okay, that's why lots of these industries and electricity plants are located next to a body of water, because they have to have a source of fresh water to utilize in their heating and cooling processes. When they're done with that water, it goes right back into the river or the stream or the lake that they utilize. That's what we see here. This is a large coal-burning power plant. This is their evaporation cooling tower, where they have fresh water that's coming in and then it runs up in all these different pipes that are exposed to the air, and it actually cools. Even at nuclear power plants, those huge structures that you see are evaporative water cooling towers in order to recondense the water so that they can pipe it back into the process to be re-evaporated into steam to move on to run the generators. Okay. In this instance, this is actually a solar power plant, and it's using a ton, again, of fresh water in order to transfer the thermal energy from its solar power into electricity, and then it dumps the water back out into the harbor that's there. This is just a rock that's in the harbor. Okay, don't freak out too much about it. Yeah, Morgan.
My town used to be powered by a power plant that was like, down the highway.
Yeah.
Beckjord. Beckjord is now shut down, and we've been seeing the economical impact of that, because now we might have to close one of our elementary schools.
Right. And so when we have these types of problems or changes within communities, when we lose a manufacturing process, there are ripple effects to that. When we close a fishery, when we have an oil spill that damages people's livelihoods, that influences the school system, it influences the diners, it influences the bank employees who then have to cut back hours because there just aren't as many people. It influences the amount of taxes that are coming into the community so they can build and maintain services for the people in the community. And that's another effect of pollution, is that when you have damaged your ecosystem to where you cannot support the economics, you start to get those social consequences. And so they're all tied together. And that's what makes finding workable solutions really problematic. because you have to solve in all those areas, or else the community, the people won't take action on it. Okay, the other big source of thermal pollution comes from urban stormwater runoff, which is the last little picture on the slide here. We all know that in the summertime in particular, when it rains on really hot asphalt, you get hot water that runs off of those parking lots, off your driveway, and it jumps right down into the stormwater system. And in lots of communities, that stormwater flows directly into retention ponds or rivers and streams. And that's a huge pulse of heat then to that particular ecosystem. It's very short-lived, but it's potentially really problematic for the organisms that live there. And if it happens over and over again, it will cause ecosystem change in that location. And I would say that's the biggest concern when it comes to thermal pollution is that given enough time to be present in an ecosystem, it will alter that ecosystem because the organisms that live there have to become adjusted to that temperature change. That's very different from what should be happening at that climate, at that latitude, at that particular microgeography location. Just two examples of some real data of thermal pollution. We're looking at lines here. There's time that's shown in the top one. We're looking at months. And then we have the temperature here. The blue line is what the temperature is supposed to be at this location. It gets warm in the wintertime months here. This is because this happens to be a dam system that's in the southern hemisphere, so their seasons are flipped from ours. And because they have a dam here, they're slowly releasing cold water from the bottom of their reservoir out into the stream downstream. And that's where this particular temperature monitoring location is downstream of the dam. And you can see that then it's much cooler, which is the actual data, is the red line here, during those summertime months when it should be much warmer because the water that's released from the dam is from the bottom of the lake, it's really cold. That means that we're completely altering the seasonality that's supposed to happen in this stream that should normally be occurring. We're completely changing the temperature for organisms right at the time when they should be doing their spawning and reproducing, when there should be a plethora of primary productivity. It's going to be too cold for lots of those processes to take place. Yeah, Caleb.
So could that be something that could be done at the ice caps? Start instead of if we release colder water around the ice caps that we created.
It could help. One thing to always keep in mind with water is that it has an enormous heat capacity. And so a change in water temperature of 1 degree Celsius actually represents a tremendous amount of kilocalories of energy that water contains or has lost. And so affecting big ocean basins like the Arctic Ocean in terms of changing temperature of anything that like we could purposefully do is very, very difficult. It comes with an immense energy cost in order to do that, whether it's warming or cooling. The other, I would say in the Arctic, the other big question is where do we get the cold water from? And so if we're one easy thing to do in the Arctic would be to pump water from deep down up to the surface in order to keep the surface colder. That's going to completely alter ocean circulation in that region, which is already changing because of the changing ice, for sure. To an extent that's potentially even more problematic than what's already happening. So yeah, we could do it. It might help. Long-term consequences, iffy. Definitely, like what I think in terms of the Arctic ecosystem is that this is a shift that's happening, and there's very little that we can do. The Arctic has passed its tipping point when it comes to sea ice cover and what's going to happen with that ecosystem. And we're seeing the move up of warmer water fishes and their associated predators into the Arctic ecosystem. And so that system is changing, and we have to adapt to that. We have to change our expectations that we're going to get out of the Arctic. We're going to lose species that live in the Arctic today because they have nowhere to migrate to. But they're going to be replaced, and that ecosystem is still going to be productive. It's just going to be quite different from what it is today. Yeah.
So the thermal pollution, like, I know it's happening. Are they trying to prevent it in any way, or are they just kind of doing it and hoping it doesn't happen?
Yeah, they're doing it and hoping and nobody notices. Okay. This is probably a hydroelectric dam, and so like the electricity generation is so much more important for this community than worrying about the changes in fish species or algae or zooplankton that are growing in the river. Not until the river starts to become unproductive for that community are they going to be worried about thermal pollution. The bottom one is stormwater warming. What we see here is there was some data from July in one year, and this is runoff and kind of the outflow pipe from a mall parking lot where they have this temperature sensor. And so on this day, they had a thunderstorm in the middle of the afternoon. This was kind of like 6 p.m. And you see you have this big, huge increase in temperature. It happens in a very short period of time, goes up about 5 degrees Celsius, which is on the order of 10 to 12 degrees Fahrenheit in the water in this short period of time as the stormwater runs off with all the heat that it's picked up from the parking lot. It's very different from the warming that should happen gradually, as happens on the next day when it's sunny out, in that same kind of stream ecosystem. It should be a more gradual rise. It can be the same amount of temperature, but it happens over a longer period of time, and organisms have a chance then to become adjusted to the temperature rather than suddenly being hit by this kind of explosion and big pulse of hot water into their ecosystem. Okay, so what does thermal pollution do to organisms? And this is why it's concerning. And again, we don't often see this, right? Like most of the time we're glad to go swimming in the water where it's a little bit warmer and the outfall can be sparkling. Lots of times you can have algae blooms and more phytoplankton productivity in these locations because it is warmer water in these locations. But that's not normal for those ecosystems. It's different from what it should be. And that's that type of ecosystem change that's happening in the Arctic. It's going to change from what it was. There'll be benefits and there'll be negative consequences. Definitely thermal pollution, whether hot or cold, is a form of habitat degradation. It's changing the quality of ecosystems. When it happens very quickly, if you have a big release from the bottom of the reservoir because there's been flooding in the area, that pulse of cold water can stun organisms. That more often happens on the hot end. When you have this pulse of hot urban runoff water that enters the lake, you can heat kill and stun thermally shock organisms. Some types of small organisms, that's it. They cannot withstand the change in temperature and they'll actually die. For larger organisms, like your bigger fish, they might have trouble swimming and they might float up to the surface where it's easy for them to be picked off by their predators. So it can, even if they can survive the shock, it often puts them at a disadvantage in their ecosystem until they can recover from the change in temperature. It definitely usually results in a reduced water quality, particularly in warming events. Hotter water is associated with higher metabolic rates. And so everything in the ecosystem is going to be running faster, particularly if you have sustained warm water temperatures in a region, like in an electricity plant outfall or from an industrial process. And as a result then, because everything runs faster, there's a greater requirement for oxygen in the ecosystem, and you end up with less oxygen in the water, which can be problematic, as we'll talk about later in class today when we talk about eutrophication. Definitely, again, extended changes in temperature alter the food web. In most cases, again, warm water increases primary productivity rates, which can draw in fish, which can make predation more severe in that ecosystem. It can cause organism migration patterns or density patterns to shift, which again causes changes in food webs and ecosystems. And that last one is that idea of altering metabolism. Again, the warmer the water is, the faster metabolic rate. Those organisms then have a higher caloric need to maintain their body temperature, and they'll eat more. The opposite happens when it gets too cold, they eat less. And so again, that starts to have food web impacts both up and down in these ecosystems, as organisms themselves change as temperature changes, and then as the types of organisms that are present in the ecosystem change as temperature changes. The picture at the top, we're looking at the outfall from a nuclear power plant. I think it's along the coastline in California. This is kind of the plant and where it sits on the coastline. This kind of white area that you see here is the infrared showing a plume of warmer water that's coming out of this electricity plant as a result of their use of water for the cooling processes. Does anyone think they've experienced thermal pollution? Yeah?
When my kid peed in the pool and it got really
Peed in the pool and it got really warm. It's a lot like that.
Sorry, it's gross, but
It
that
happens.
plume made me think of it.
Yeah, it happens. It's interesting, again, it's something that you can't see because it's a change in temperature. But as we start to look for it, we recognize that it's actually happening pretty frequently within our aquatic environments, particularly in freshwater ecosystems, where we have lots of dams and channelization. That changes water velocity, changes water depth, and those things, in addition to how we're pulsing and moving freshwater in these ecosystems, changes temperature. And that's a fundamental variable of what organisms can live where and how many of them there are. Okay, all right, our next topic and type of water pollution then are pathogens. And what is a pathogen? Right, anything that causes disease is what we're gonna go with in our class today. And kind of as we talk about diseases going forward, there are all kinds of pathogens, right? It can be bacteria, you can be a virus, you can be a eukaryotic parasite, you know, you can be a worm, you can be a tick. All of those things are potentially disease-causing or moving disease-causing organisms around in our environment. Sewage, like the sewage outfall that we see in this particular picture, is a major source of pathogen pollution in aquatic environments, both freshwater and saltwater.
That's sewage.
That is sewage. For a long time, kind of over the course of human history, water and dilution of sewage waste in water has been our solution to our pollution problem when it comes to sewage. And that you dump your waste in water, it gets mixed and diluted, and it flows away from you. Okay, and that means that it's gone, right? And it's less likely to be problematic. That worked really well when there weren't too many humans on the planet. And now that there's a lot of humans, now that we have a lot of organisms that we farm and grow alongside of us to help us sustain ourselves, we make a ton of manure waste, okay? And we have overwhelmed the dilution capacity of most of our aquatic ecosystems to deal with this waste. And as a result, we get really high concentrations sometimes, potentially deadly organisms to us, aquatic organisms, to things like cattle and sheep that are also utilizing freshwater resources in the water that is meant for drinking and sanitation purposes. Okay? In this particular sewage outfall, this is one outfall in Florida, in South Florida, that collects and combines the waste from 3 different treatment plants, and it discharges about 360 million gallons of diluted and processed sewage waste onto the coastline every day. I have a couple pictures from this that we'll see. Yeah, he's like, that's gross. It is, all right? We'll have a couple pictures from this. Of course, the different scuba divers were highlighting this problem and kind of reminding the public that this is what happens to our waste. Normally, I don't think many people would be swimming around this particular outfall, but they were interested in taking pictures to put in the newspaper for it, so we get these types of pictures. Why is the water green?
Not just water.
Good. So what is in the water that's making it green? Like usually when we think of sewage waste, we think about it being brown, right? So like, why is this green?
Is it something that's breaking down,
Not breaking down,
already broken down?
growth, okay? It's growing algae, okay? The nitrogen and phosphorus that's left after sewage treatment at this location promotes the growth of algae, okay? And there's tons of algae in this water that's growing, and then it's being expelled into the marine ecosystem. That kind of green water is a classic sign of sewage or manure pollution in a location. It means that you have excess nutrients for plant growth, and the algae, the plants are growing. Okay. It's a tracer then for the other types of pollutants that can be in sewage. Okay, so where does this stuff come from? Again, the pathogens in sewage is coming from human and animal fecal waste for the most part. Okay? Your digestive system, that of the animals and livestock around us, is laced with all kinds of microorganisms, most of which are completely harmless, some of which, though, can cause disease when ingested again. Or if you have an infectious disease, this is one of the ways that you often shed it, is in your food. If left untreated appropriately, those pathogens run off and end up in our freshwater and saltwater resources. Sewage treatment plants are designed to break down the solid waste particles. They do some filtration and UV radiation and chemical treatments to kill pathogens, so that the water that they release should be safe, okay? They don't usually do anything to clean up excess nutrients. And in lots of cases, when we have a stormwater event, it overwhelms the sewage treatment plants, and untreated sewage gets released directly into the environment with its full complement of pathogens and waste flow. Okay, so that's where this stuff comes from. Sources, of course, sewage treatment plants, septic tanks that are leaking or that are pumped out and then the waste disposed of. Definitely livestock manure and pet waste that's left on the ground. When you have a precipitation event then, and that stuff gets mixed into a slurry, it runs off the ground and into water resources, and then stormwater overflow can be a big problem. When I lived in the city of Seattle, we had lots of rain, right? Okay, if you think we had a great stormwater system, that would be a no. Okay, we had some stormwater reservoirs and resources, but it was directly piped into our sewage and sewer pipes. And so when we had heavy rainstorms, it would overwhelm the sewage treatment plants and the reservoirs, and we would end up dumping untreated waste directly into Puget Sound. Okay, like the bay that we were in there, where all of that went into the beach and utilized. Like the place where we used to go with my twins in order to like throw rocks in the ocean, which like trust me, if you have 3-year-old twins, it's something you want to do as frequently as possible. There was this huge pipe there, and it said if it has just rained, don't come to this beach because there's sewage flowing out of that big pipe. Okay, is that pipe great? Okay. And so one of the things that Seattle has had to do is build new stormwater treatment plants just to deal with this problem, so they stop releasing potential pathogens into the waterway that everybody in the city utilizes. Okay, and they have done that, but it's very expensive, and it costs the citizens of Seattle and the surrounding suburbs in order to do that. Okay. The other thing to remember when it comes to this is that we're lucky in the United States that most of our communities treat sewage in one form or another, and there are different levels to sewage treatment. For most communities around the world, there is no sewage treatment plant, okay, and they're directly exposed and interacting with their waste on a daily basis. Okay, as per the U.S. EPA estimates, every year in the United States, 1.2 trillion gallons of sewage from household, industry, and restaurants is dumped in U.S. waters annually. According to UNICEF, more than 3,000 children die every day globally due to the consumption of contaminated drinking water. On average, 250 million people worldwide succumb to diseases related to water pollution. It's the major cause of various diseases like cholera and typhoid. And here in the U.S., 40% of rivers and 46% of lakes are polluted and considered unhealthy for swimming, fishing, or aquatic life. It's a big deal, okay? It's not just a problem in rainy Seattle. Okay, so what's problematic about this? First and foremost, the sewage discharge contains disease-causing organisms. It contains viruses, bacteria, and those eukaryotic parasites that I mentioned. Cholera and typhoid are definitely bacterial diseases. Some types of intestinal parasites are things like Giardia. Those are eukaryotic little spitty guys. Yeah.
Is there any way for them to treat viruses out of the water?
No, viruses are very, very hardy to the types of sewage treatment that are available, usually in primary and secondary sewage treatment plants, which is what most communities do. Tertiary sewage treatment plant requires that you hold the sewage in a retention pond for several weeks to several months. And in that time period, while the nutrients are being chewed on by microorganisms, usually the viruses get broken down due to interaction with ultraviolet light too, just from sunlight. But it just takes a long time.
Viruses are harder than the human bodies.
Right, exactly. And it, to really treat for viruses, you need to alter the pH of the sewage, and that's, again, that affects then when we're going to dispose of that water. And so that's something that we traditionally have not done or worked on. The other problem with viruses is that they're very, very tiny. And so to filter them out takes a long time and makes the process of sewage filtration even more energy and money expensive. So again, it's easier to dilute out these problems by dumping it into a large reservoir of water and then in that way reducing the concentration of viruses and potential pathogens rather than trying to fix it in the kind of either source or in the sewage treatment plant itself. Lots of these potential pathogens can jump across species. And so viruses of humans can infect organisms that are out in the marine environment and cause problems. We've seen a big problem in marine mammals and coastal communities where we have high incidence of rabies that are moving from pet populations and wildlife populations on the shoreline into marine mammals. They're getting viruses that are related to canine and feline viruses. And we can track that back to untended pet waste that's washing around in the ecosystem. These types of instances, when it's recognized that we have a large quantities of potential pathogens in an ecosystem, we test for that on places like beaches, and we test for that in sewage outfall. And we have regulatory standards about how much E. coli can be in a particular water sample. And when it gets too high, we have to close those recreational places. We have to shut down water intake into our kind of water treatment plants because it's dangerous to use that water. And so there can be economic consequences, there can be recreational consequences to this. Again, in Seattle, when we have a bunch of these rain events, lots of times the fecal coliform level goes up in some of the lakes that everybody likes to go to around Seattle, and then you can't go there either, okay, until the city tells you that it's safe to go in the water again. The other thing that I want you to recognize is that sewage today contains not just our waste, kind of from our own bodies, but it contains leftovers of everything that we put in our bodies. Okay, and that means that the chemicals and the pharmaceuticals that we expose ourselves to on purpose, lots of times, the excess that our body doesn't take up goes down into the septic system. Okay, you're going to take an overabundance of antibiotics usually to make sure that you kill the infection that you have. That's very useful, but what your body doesn't take up, you pee and poop out. Okay, and it goes into the water. Okay. And we're seeing that there's an increased number of pharmaceutical chemicals that are in particularly freshwater ecosystems close to communities. And this has impacts on organisms in those ecosystems very similar to the impacts that those pharmaceuticals have on people. Okay. Which is both kind of cool, like, wow, fish can be affected by antidepressants too. And it's also very, very disturbing because there are consequences to treating entire fish populations with antidepressants. Okay. So an example of this is the presence of pharmaceuticals in sewage. We're looking at different, so this is a smallmouth bass, and this data is all for smallmouth bass. We're looking at the percentages of male smallmouth bass in different rivers in the northeastern United States that are transforming from males, which are all these little tiny sperm, into females. They're starting to develop oocytes or eggs in their gonads rather than sperm. And this is because they have been exposed to birth control drugs. Okay, like it is affecting these steroids fish in kind of similar ways as it does to humans, and in some unexpected ways. Okay. This is problematic for fish populations. If 100% of your male bass are female now, there will be no males in which to fertilize your eggs, okay? Which means that your bass population is not looking too healthy in the near future. Well, then they'll lay their eggs. Lots of fish are actually pretty malleable when it comes to sex, or gender, I should say. And so whatever is in their reproductive organs, whatever in their gonads, is going to get dumped out into essentially their cloaca. They're very similar to birds in this kind of sense, and they'll expel eggs instead of sperm. There are several types of fish that switch gender over the course of their life based upon age and size. Yeah, some anemone fish like Nemo can switch gender, again depending upon kind of social fish situation, and usually it's size. And they go both ways. There are some that go from being female to start males at the end of life, and some that start out as males and they end up being females at the end of life. But this should not be happening normally in this vast population, okay? It's due to exposure to steroids and leftover pharmaceuticals in the water. The other really interesting one comes out of Scandinavia, and they had a pharmaceutical plant that was producing antidepressants. And they started measuring antidepressant levels in the river next to the pharmaceutical plant, and sure enough, there were measurable amounts of this compound in the waterways. And they started looking at the fish in the river, and sure enough, the fish were feistier. They were less shy. They were less anxious. They were out there doing their thing because they were less depressed, okay? Like they were having the similar effects to humans of this drug, chemical. And that's potentially good for the fish, like they're gonna get more mates, they might actually mate more frequently, increase population numbers. It meant though that the fish were more voracious. It meant they were out there eating more. And that's bad for the food web. When you have a predator that suddenly starts eating more prey items, you start imbalancing again loss of your ecosystem food web. And this is a new kind of area, I would say, of research when it comes to sewage water pollution, is looking for pharmaceuticals in water and trying to determine what the source of that is, whether it's disposed of medications, whether it's the population that's receiving these doses of medications, whether it's the manufacturing process that's producing them, and seeing if we can start to control potentially some of these point sources of pharmaceuticals and be aware of their presence in the ecosystem around us. The other thing to think about is that this is the water that we drink, okay? You're being exposed to these compounds and chemicals oftentimes because these are not things that we treat for in water sanitation or sewage systems. Yeah?
How much does a water filter do in situations like this?
It really depends on your water filter. Most water filters are doing 3 things. They're taking out sediment, so your water's clear. They're taking out ions, they're taking out metals so that your water keeps good, and or that kind of hardness, softness range that we think about with water. They're doing that type of chemistry. And they're filtering out pathogens. They're taking out bacteria. And in some cases, there are really good water filters for drinking purposes that will take out viruses too. And they're not at all doing the type of chemistry that's able to remove pharmaceuticals. Okay. Any questions about pathogen It makes you, again, it's one of those things that I think makes us aware of what it potentially is in our water and what effects that has on organisms as well as then on us. Okay. Sewage waste is very closely linked not only to pathogen pollution and pharmaceutical pollution, but it's also very, very linked to eutrophication, which is the last big topic that I wanted to touch on in water pollution and this aspect of water ecosystems. And eutrophication, very simply, is the enrichment of a body of water with nutrients for plant growth. Okay, and usually it's nitrogen and phosphorus. And it takes a little bit of a combination of both of them in order for plants really to grow. In saltwater ecosystems, nitrogen is usually the limiting nutrient for plant growth, whether again it's little phytoplankton or large things like kelp and kind of algae mats, bigger types of produce eukaryotes. In freshwater ecosystems, phosphorus tends to be the more limiting nutrient. But they need both, and they need them in certain ratios to each other in order to do very, very well. The enrichment then of nitrogen and phosphorus in a body of water causes the plants to grow. You get those pictures of those green waters, those algae blooms. And when we say bloom, we're saying that an organism has rapidly increased in abundance. Okay, so a bloom is when a population of organisms rapidly increases in abundance. And depending upon what's there to start off with, whatever primary producers in that ecosystem will increase in abundance as a result of giving it fertilizer, giving it the nitrogen and phosphorus that it was lacking. Yeah.
Some of that stuff we poisonous and toxic.
Yeah, exactly. So some of these phytoplankton in particular And when they get into high abundances, they start to give off toxic chemicals that deter their predators, whether it's fish or zooplankton. And so then it becomes a harmful algal bloom, okay, or a HAB. And some of those toxic chemicals can cause respiratory distress in humans, and they accumulate, just like toxic chemicals can of other types, in filter feeders, in things like clams and mussels. And so then when we eat those organisms, we have to be aware of our potential exposure to those toxins and those poisons. And so paralytic shellfish poisoning, of course, is one of these things that can happen if you eat an oyster raw that has been exposed to and been eating these types of toxic phytoplankton, you expose yourself to those toxins too. Okay, so that's why there's always that little like jingle about when it's safe to eat raw oysters. Don't eat them unless that end with R, or like have an R in them. Otherwise, it's fairly safe. Okay. The best solution is to cook your oysters first. Okay, I think fried oysters are very good. Or just not eat them, right? That's another thing, just not eat them. This can happen too. You can get these types of toxin accumulations in things like the muscle fibers and some big predatory fish that we like to eat too. So in kind of the Gulf Coast region, you have to be aware of Cigatura fish poisoning, which is when some of these harmful algal bloom toxins accumulate in things like grouper and snapper and barracuda that you might be eating when you go and eat seafood in these locations. The classic thing is that if you feel any tingling in your mouth while you're eating seafood, spit it out, okay? Not a good sign. Okay, that means there's something in it that you probably shouldn't. Okay, that's the PSA for today. Maybe that's a safe rule. If you feel any tingling in your mouth while you're eating anything, not a great idea. Okay. All right, unless you like pop rocks, yeah. Yeah, we don't need to go down the pop rocks pathway.
It's very organic.
Eutrophication is a natural process, okay? And this is where, again, we can have a dissonance sometimes between what's happening in the academic community and happening in ecosystems and what's happening today. And I hope to make that clear for you when it comes to eutrophication. Eutrophication is a natural process. It's a portion of how particularly freshwater lakes and streams age and change over time. In any lake, you're going to have an input of nutrients into that lake. Phytoplankton and other primary producers are going to grow. As they do so, and particularly if it's something like a marsh grass or a shoreline reed, a cattail, it's going to accumulate sediment around the roots of that organism. Even as phytoplankton die, their bodies build up sediment and soil at the bottom of the lake. And the lake slowly eutrophies. It slowly fills up over time and gets shallower and shallower. The lake penetrates farther and farther down closer to the bottom as it gets shallower and shallower. You get even more phytoplankton growth. And eventually, that lake will completely fill in and it will be land. Okay, eutrophication is a normal process in the aging and filling up of lakes and the growth of plants in those lakes. You go from deep water lakes to shallow lakes with more and more plants in them, and as you do so, the species of organisms that utilize that lake change over time. This can also happen from aquaculture, and aquaculture is when we grow fish or marine organisms, things like shellfish and shrimp, purposely in enclosed locations. And in aquaculture, we make a ton of waste. Okay, that will eutrophy the area in which that happens. All that manure waste from whatever fish or shrimp that you're producing has all the right nutrients in it for phytoplankton to grow. Okay. Notice though that the time frame for natural eutrophication is centuries. Okay, it should take centuries for a lake to fill in and eutrophy, for the water quality and depth to change. Cultural eutrophication is when humans accelerate the natural process of eutrophication by adding even more nutrients into that ecosystem. Okay, the effects are the same. We increase plant growth, we increase the amount of sediment flowing into a body of water, it will eutrophy and fill up over time. Okay? Notice the time frame. Decades. Okay? We're doing this much, much faster when humans get involved. And that is the major difference between normal eutrophication and cultural eutrophication. not only the source of those nutrients, but the time frame. Humans accelerate the process to make it go much, much faster than it should. And there are consequences, ecosystem-wise and ecosystem services-wise, for cultural eutrophication. In your homework assignment, I think I've graded everybody's and I've gotten everybody's back to them, except for one person here in class. So you should see your grade for homework 1 on Blackboard now. Everybody did fine. One of the big things I wanted you to notice in that homework is that we've changed the types of pollutants that are in our freshwater ecosystems. We've gone from industrial pollutants, oil, petroleum, lead, mercury, chemicals coming out of plants, to eutrophication pollutants, to excess nitrogen and phosphorus as the dominant types of pollutants in most of our ecosystems. Yeah?
Well, there's another thing with like flooding and drought, because like now that everything's getting shallower.
Yeah, it doesn't help at all. Because of cultural eutrophication, because of the filling in, because of excess plant growth, then it's easier for a flood to happen. There's less capture. Okay, it also means there's less reservoir there when you have a drought. Okay, they're all linked together. We talk about them like they're separate things. Okay, where do we get these nutrients that cause cultural eutrophication? First and foremost, municipal sewage. We talked about this. It cannot and do not do a good job of treating for nitrogen and phosphorus that come out of our human waste. As more and more of us live together and produce waste together, then we have concentrated output of nitrogen and phosphorus at the end of our sewage treatment processes. That causes that green algae growth in those sewage outfalls that we put in. Okay. Agricultural fertilizers. We add a tremendous amount of nitrogen and phosphorus onto our agricultural fields in order to enhance plant growth. We've got to do this in order to produce the food that we must have as a human civilization to survive. When we do it in excess, when we apply that fertilizer inappropriately, the excess of it washes off into freshwater ecosystems and causes eutrophication. The third major source of nitrogen and phosphorus is livestock waste. Okay? A lot of our ranching processes are dependent upon very limited retention ponds to hold manure waste, and that stuff cannot degrade quickly enough on the land so that a ton of it gets rinsed off into the nearby ecosystem where it's diluted and becomes a source of nitrogen and phosphorus. And so downstream, lots of times, of ranching practices of poultry production are big, big problems with cultural eutrophication. Stormwater drainage and aquaculture are also potential sources, again, of untreated sewage or manure waste that could be a source of nitrogen and phosphorus. But they're down there on the list of these sources. Okay, so that's where this nitrogen and phosphorus is coming from. All right, it's coming from agricultural runoff. It's coming from sewage, either from humans or livestock. Okay, so what happens? All right, this is the process of eutrophication. Okay, it's not that big a deal, and it happens very naturally and normally in these ecosystems. But one of the things I will ask you to do for sure on our first exam, which is in like a week and a half, okay, first morning, about the first exam. Don't forget. I will ask you to list for me the steps in eutrophication. Okay, first and foremost, you have to have nutrients added. Here it's runoff that's coming from the agricultural fields. Okay. The second thing that has to happen is that those nutrients have to end up in a sunlit water layer. Okay. You have to have sunlight. You have to have shallow water for this process to take place. Those two things together, the nutrients and the sunlight, mean that the algae bloom. Okay, it could be a diatom, it could be a dinoflagellate, it could be a cyanobacteria, it can be, there's a whole bunch of types of seaweeds, okay, that fall into the category. They have to bloom, they have to increase rapidly in abundance because they have the things they need to photosynthesize. They have the nutrients and they have the sunlight. All right. The fourth thing that happens is that not all of those algae get eaten by fish or zooplankton, okay? Because they bloomed in abundance, they overwhelm their predators. And a bunch of those algae, they sink, I should say they die, and they sink down into the bottom waters of the lake, okay, or the coastal ocean, okay? So the algae bloom, they don't all get eaten. Those that don't get eaten die. And when they die, they lose their ability to remain buoyant up in the surface waters, and they sink down in the water column, okay? So far, no problems other than whatever is happening. The water's turned green, it looks gross, and we've got some toxins. It's not terribly bad when it comes to the problems. The biggest problem comes in the last step, which is in pink and hard to see here. The algal decomposition of all these dead algae reduces the oxygen concentration in the water. Okay? All those dead algae now that are at the bottom of the lake have to get decomposed. And they do. There's all kinds of bacteria and microorganisms down there that will happily eat these dead phytoplankton. That's where the big problem with eutrophication comes in. Okay? That microbial decomposition sucks all the oxygen out of the water in those deep layers. Okay? And that's very problematic for these bodies of water. Okay? Not only have we disrupted the normal kind of flow of nutrients and organic matter through the food web by causing this big bloom of algae, but now we're drastically reducing the oxygen concentration in these waters. Why would low oxygen concentrations in the water be problematic? Yeah. Yeah, other organisms need oxygen. What kind of organisms need oxygen? Fish. All the things we kind of care about, right? Okay, crustaceans, clams, oysters, starfish, sea urchins, okay? Fish and dolphins like don't breathe in the water, right? They have to come up to the surface. But dolphins are there because the fish are there, right? Okay, so like dolphins and sea turtles and fish, they can swim away from these low oxygen areas if they're able to do so. Okay, if it's a lake and you're confined, you really can't get away from this. If you're an organism that's stuck in place, you're a mussel on a rock, and the oxygen level gets too low, that's it. Okay, you die. And that's the big ecosystem problem with cultural eutrophication that causes hypoxia and anoxia, causes these dead zones to develop at the bottoms of these aquatic resources where there is no oxygen. And the bottom of the food web, the base of the food web, these types of filter feeders get killed off. Okay? And that's bad for water quality. These are filter feeders. And it's bad for the food web because we're taking out a vital link of moving organic matter from primary producers kind of up towards the organisms that we're interested in. Plus, if one of the industries in your area is harvesting these types of bottom-dwelling sessile organisms or slow-moving guys, and they all die, that's bad for your fishing industry. Okay, so essentially what's happening is what we call an increased biological oxygen demand. So this is a term that your textbook utilizes when talking about eutrophication. We increase the BOD, the biological oxygen demand. I'm introducing that term to you, biological oxygen demand, because it's something that comes up frequently when we're doing environmental science, when we're assessing environmental quality. We need a certain level of oxygen, which is usually measured in kind of parts per million out in the water in order for organisms to be able to survive. When it gets too low, then these organisms can't be there. Okay. The long-term consequence of eutrophication in an ecosystem is the production of dead zones. And this is where organism death or migration occurs in an area due to increased biological oxygen demand and the resulting reduction in oxygen concentration in the water. Yeah, sure.
Are there any species that like migrate in?
Yes, so particularly in the Gulf of Mexico, we have this huge dead zone at the end of the Mississippi River today. It's like the size of Connecticut and New Hampshire put together. That's a result of all this agriculture and sewage waste that flows out of the Mississippi River basin. There are lots of organisms that normally migrate on a seasonal basis around with the currents of the Gulf of Mexico. They're swept or moved purposefully into this dead zone where they're supposed to be safe or able to eat at that particular time of the year, and then they can't. And in some cases, they swim out, hungry and looking for something else to eat somewhere else. In the case of things like coral larvae and oyster larvae in this location, those baby organisms are wanting to settle down in this dead zone. And when they do so, then they die almost immediately. All right. So you get these dead zones. We call it hypoxia when we have low dissolved oxygen concentrations in the water. Hypoxia is usually somewhere between 5 and kind of like 0 parts per million dissolved oxygen in the water. When you get no dissolved oxygen in the water, it reads 0 on your instrumentation. It's called anoxia. Okay, an means without oxygen, the oxygen part here. When this happens, when you get low oxygen concentrations, you immediately disrupt your food webs. You have more organisms leaving, you have organisms dying. That will not be reestablished until the water gets oxygenated again. And this usually happens on a seasonal basis. Lakes turn over, right? You have cooling of water at the top, which makes it safer, the oxygenated water will sink. You can have a storm event that will mix oxygen into these anoxic or hypoxic waters. It just depends on how long it lasts, how bad the disruption is. When the algae or the phytoplankton are growing themselves, you can get those harmful algal blooms that we've been talking about, or those hats. The fish in this particular picture are menhaden that died to a severe hypoxia event along the coastline. It was severe enough that they died, and then you get all these dead fish that wash up on the shore. That's extra gross. Okay? Yeah, that's super fun. These fish then, usually, they're not marketable. They've been dead for a little while. They're starting to spoil, and the community has to clean them up. They lose the tourism while they're in the process of cleaning up the fish. For many of our coastal locations here in the United States, these events are well established, and tourists know when they're likely to happen, and then they stop going to those locations at times of year. Usually in summertime, early fall, when these events tend to happen. Along the inland bays in Delaware, where I was doing my PhD work, we would have these events where these anoxic bubbles would bubble up from the bottoms of these inland bay resources due to eutrophication. And when the water turned over like this, all of a sudden you'd get this burst of low oxygen water that would come to the surface of the bay and kill all of the fish. And so you'd open up your porch one morning out in one of these bays, and there'd just be this big fish kill filling the entire area because of this bubbling event. It stinks. It's gross. It spreads and promotes infectious diseases throughout the fish community and other communities as well. It disrupts the food web. It disrupts fisheries. Its start is really insidious, okay? It's not something we can see or that we can easily test. Okay, this is the global increase in the number of hypoxic zones around the world. The data is not relatively recent, but in general, there's about 762 sites across the globe that are recognized as having usual hypoxic or anoxic events. All of the red dots and yellow dots are places where we have documented cultural eutrophication and this decreased oxygen concentration in the water. Why do they all occur along the coast? Rivers coming out there. Okay, they're dumping their big load of nitrogen and phosphorus right off the coast. Why else are most of these coastal in location? Populations. Okay, that's where people live. That's where we're generating this type of pollution. That's where it's going to have an impact. The other thing about it is that it has to be shallow, sunlit waters for this process to take place. That's along the coast. Okay, it's not going to be out in the open ocean where it's too deep and too dilute for this to take place.
Can you go back to the last one?
Yeah.
So this is obviously like exponential growth. Has it continued at that kind of rate
Yes.
since?
Yeah.
That's good.
There is a bit, in both this data and this data, I would say there's a bit of what we call observation bias. Now that we're looking for it, it looks like it's increasing really rapidly because we're looking in more places. It may have been there since the 1980s in lots of these locations. We just weren't testing, looking for it documented. Okay. Of course, at the end of the Mississippi River, as I mentioned, we have this enormous hypoxic zone. This is, again, we're looking at oxygen concentrations in the deep waters at the outfall of the Mississippi River. In this location, again, the Mississippi River comes out, carrying all of our agricultural productivity excess with it, major population centers in terms of sewage outflow. When the Mississippi River gets out here, it dumps its water and its sediment out here, and then the major flow here is back in this location. And so it drags this hypoxic zone along the coast of Louisiana and a little bit of Texas. Okay. Again, this area is encompassing the size of New Hampshire and Connecticut put together. It's an enormous region that used to be highly productive in terms of shrimp as well as oyster fisheries, and has become increasingly less so as the size and the extent and the severity of this dead zone has increased over time. Yeah.
So is there a lot like dead Mississippi rivers? Or just like pollution or something like
No. I mean, if you go to the Mississippi River, it's a lot like the Ohio. So I haven't been on Mississippi in a while. When I lived in Arkansas, we were constantly like going to and from Memphis, and so we were crossing it a lot. I've been to the headwaters in the Mississippi, which are clear and beautiful, and tiny in comparison to the rest of the Mississippi River. The Mississippi River doesn't have any more like dead stuff floating in it than say the Ohio does, I would say. It's muddy and brown, just like the Ohio, shows this really high sediment load. That's indicative of this agricultural runoff. What I would say in the Mississippi River is like the Ohio, the types of fish have changed dramatically. From organisms that used to live in clear waters to organisms that do great as bottom feeders, detritus feeders in these types of high sediment load, high pollution load water. The ecosystem has changed. This is the size of the hypoxic zone in the Gulf of Mexico. There is some variability in it. It's doing better recently as we started to recognize that this place exists. We started to do a little bit of a better job regulating nitrogen and phosphorus input into the Mississippi and started to order to the Baltic Sea has problems just like this. The Chesapeake Bay has problems just like this. Hudson Bay has problems just like this. Any large freshwater coastal resource that has nutrient input to it is suffering from cultural eutrophication. Again, the ecosystem change can be really dramatic, and where there are important fisheries in that location, either for economic purposes or for human sustenance purposes, this is really problematic. It's a huge change in water quality. It takes a lot to clean up. We have it here in the Great Lakes ecosystems, particularly in Lake Erie, which is one of the shallowest of the Great Lakes. We have these huge algae blooms that happen every summertime in Lake Erie. Sometimes they're problematic, sometimes they're harmful. They are a sign of ecosystem change. Okay, what I want you to do today is find some partners. I have materials for 6 groups, so at least like 3 people in your group today. Try to form up with another pair. Now that you know about all these potential sources and problems with pollution, I'm asking you to design a watershed. And I can't remember if we did this last semester or not, you guys. But this is where it works best. So you have, I'm going to give you a river. This is your river. All right, it goes like this. All right, this is north. This is south, it has a little compass on it. Okay, everybody gets a river. You have to put these 8 things along your river. Okay? You have a park, an industrial park, and a bunch of plants that are doing industry, some irrigated agricultural fields, a water purification plant, a sewage treatment plant, some houses, a hog farm, and a hydroelectric dam. Okay? All these things use water from the river, and they're going to put water back into the river. I want you to talk to your partners and see if you can arrange them along the river in a fashion that makes sense. Okay? There are a couple rules. Okay? Pigs grow slower, hear loud noises regularly. Okay, so like, that might limit where you can put your hog farm. Okay. The other thing is that, you as the city managers have promised the citizens that you'll put the park next to the homes. Okay, all right, do it. When you get your, items, put your names on the back of the river, okay? And then you'll grab some scissors and tape, and you can cut them apart and stick them on your river, okay?